Okay, shall we start?
Yes.
Can you see my screen, or
What?
you can't see my screen yet, right?
No.
Okay. Let me... Okay, now you can see my screen. Okay. Do you hear me? Hello? Great. I don't know if you can hear me. Everything's frozen now. As soon as I shared my screen, everything froze. Okay, you're back?
Okay.
As soon as I shared my screen, everything froze.
Oh, connection now is back.
What?
Okay. Can I share your screen?
I'm going to try it again and hope that it doesn't all freeze now.
Okay. Let's see your face.
Okay, I can still hear you and I can still see that my screen is being shared. Okay, let's go then. Aren't you?
Yes.
You ready to go?
I mean, I cannot see your slide.
That's because I haven't shown you my slides yet. But you can see you, right? Look up there behind you.
Yeah.
That's my screen.
Yeah.
Okay. Am I broadcasting?
Yes. You can
Hear
start.
me?
Yes.
Okay. Okay, and you can see my slides and everything's hunky-dory now, right?
Yes. Can see your slide.
Okay. All right, so last time we started talking about MDPs and we got as far as value iteration. And just to review again, a Markov decision process is a set of several things: a set of states, a reward function, a set of actions, and a transition function that gives you the probability of reaching state S prime given that we're in state S, and take action A. Okay, that defines an MDP. Some of those states, well, like one of the states might be an initial state, and some of them can be terminal states where life is over. And again, this is what you should have in your head. We're going through this state, action, reward, state, action, reward. Okay, we did all that. And then we have this standard MDP from Grid World. This is just one example. You should not like take all of Markov decision processes to look like this Grid World. But I wanted to just make the point here that this little picture over here is the transition function we've been talking about. This is the probability of getting to state S prime given that you're in state S and you take action A. Basically, it's the same for all of these squares here, except when you get to final squares. So this defines the transition function. Okay.
Okay.
And it's Markovian in that you never your past is over once it's over. Okay. So what we're trying to figure out is the optimal policy, and the optimal policy depends on the utility of a state. And in this case, we're going with a stationary policy, an infinite horizon, and so we're going to use discounted rewards like this. And so the utility of a state sequence, the utility of a particular state is the expected reward that you get following the optimal policy. And so to compute that, we have to know what the value of each state is. So let's see, where do I talk about the value of a state? Okay, yeah, so here's the utility of a state. It's the reward you get in that state plus the discount factor times the expected next state. So this is again our little 0.8, 0.1, 0.10 guy, and the utility of the next state. And again, this is a recursive function. It's got u on the left-hand side and u on the right-hand side. But once we get that, we can choose the optimal policy by taking the action that's going to maximize our expected long-term reward. Okay, so let's see. So this would tell us what to do. We should take action A if it maximizes the transition function times the utilities of the next state. That actually defines the optimal policy. Assuming u here, u for this state that we're in and u for the next state we're in is known. Once I know the utility, then I can define the optimal policy for each state as the one that maximizes this little guy. And again, this is the Bellman equation, and it's a nonlinear equation. And so we need to use something non-obvious to solve it. And remember, this is a set of equations. So there's, let's see, in the grid world we're in, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 states. The value of these final states is fixed. So really, I've got 9 states that I've got to figure out the utility for. And to do that, I iterate the Bellman equation. So I start out with utilities being 0 for all 9 of those states that I don't know, and then +1 and -1 for those 2 states that I do know, because those are exit states. There's no actions I can take inside of those states. And then this is defining the optimal policy. I already said that. It's the action that maximizes this, this little guy. Okay. So if we knew the values of each state, we can determine the optimal policy. We find the values by value iteration. And most of this is talking about when do I stop? But the real thing here is this update. Instead of using this as an equation, I use it as an update of the utilities. So I start with all the utilities being 0. And so all of these are going to be 0. The only thing that's going to happen is the reward in each state is going to be the initial utility for every state, because we start with everything 0. There's a 0 here, and so everything here is 0. And the max action is going to be any one of the actions times the discount factor. So, so this is all going to be 0. And initially, the first step of the algorithm is just going to initialize all the utilities of all the states to their reward. Then after that happens, now I actually have numbers here. Assuming I have rewards in every state, some states might have 0 reward, depending on how the problem is set up. Then I'll have something here, and I can pick the maximum action for what I should do next. Again, if there are ties, in this case, you can just pick a random one, and then you update. And so what happens is, if you look at this, maze example, initially all of these are going to be set to -0.04, because that's what we've been using as our reward. This one's going to be set to +1. This one's going to be set to -1. And the guys right near here are going to get most updated first, because you're going to find out that if you go right, you get this really big reward. And so, again, the correct utilities, it won't be the final utility, but they'll spread like from here like ripples on a pond. And I'm going to show you that this time. Last time I couldn't do that because that demo didn't work. But I found a lecture on the web where some guy iterates that demo. And so we can actually do it. Are there any questions about this? Okay, so here's this actually converges, and it converges because the Bellman updates a contractive mapping. That is the utilities of 2 states, or sorry, the utility of a particular state, the difference between some value of it and some other value of it is shrunk by the Bellman update. And this is what you get. You can see that the guy nearest the final state gets updated most quickly. These are just some examples to the goal, get updated most, and then it spreads out to the other guys. And the last guy is use the one that's farthest away to start getting the real value, is 1, 1. Okay, so I'm not going to go to Safari. Instead, I'm going to go. So this is the guy who got this to work. Let's see, and I've got recorded where I want to go. 9:35 and 11:09. Let's look at that. So we're going to hear this guy while he does this. So this is an initial state where nothing is known. What's being shown here is the current value in the little corner here, and then the estimate of the best policy, which could be up, down, left, right, but right now there's no, we don't know what the best policy is because we haven't got any values. And so as we iterate, do value iteration, we can estimate the best policy as we go. And we can watch these turn into a good policy. So let's listen to this guy for a few minutes.
So like I'm here and I'm wondering which way to go. I look at the value. It's equal everywhere. So I don't go anywhere. I don't have my policy is like, I don't know. We have 0 everywhere. So I do one step, one Bellman backup. Ching. And so now the value function will reflect just the immediate reward at each state. Right, so we have -10, -5, that's +10.
So right here, he's just, there are 2 bad terminal states here. This one is -5, this one is -10. There's a really good terminal state here that's +10, I think. And this one is +3 up here in the corner. And then you get negative rewards for hitting the wall in this little world. So that's why the outsides have some numbers on them.
That's +3? Yeah. Yep. Stay away from the walls in this world. Ouch, that hurt. Value iteration. King.
Okay, so that was updating the Bellman equations. And you can see that things right around this good goal have now have a good estimate that if I go this way, that's good. This guy says if I go this way, that's good. Nothing much has happened here because this is a world in which you can only make Manhattan-style moves. You can't move diagonally, so these guys don't know that. And notice around this path thing, all the moves that would move towards it have gone off, basically. Similarly here, all the walls hurt to hit them, I guess, and so you move away from them. And around this medium good state, everything's trying to go into it as well. Okay, so that's the first step, the Bellman backup. All the numbers that are 0 are being propagated to the ones right next to where we knew what the values were. Those have updates. And look, here, last time we found out, now it's telling you to stay away from those around the outside. Okay? So we just updated the Bellman equation 1, 2, 3, 4, 5. This is a 10 by 10 world. We did 100. We had 100 equations, and one for each state, and we just updated the value for each state by the Bellman update equation. Okay, and then he talks for a while, and let's go up to where things start happening again.
So you can see the value function start to take shape as we do more and more steps of value iteration. Again, 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 and 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 again. You can see the numbers are starting to go down, actually. Changing that much. If I press it a lot, now they're, yeah, now they're stable. We've reached equilibrium.
Okay, so that's your demo. Sorry, I'm not in control of it, but now all these numbers, these value functions, these value utilities state have converged, and you can see this one has low utility because basically it's going to take some hit before it gets to here. So again, this is, if you look up here, this is the expected long-term reward from this state. If I follow the optimal policy, I can expect to get 0.94 goodies. And here it, when you get close to a goal, if you're already close to a goal, it's a short hike and you don't get as much discounting and you have a better outcome. And from any state, like this one down in the corner, the best thing to do is to head usually to the state with the next highest value. Okay. So that's value iteration. Any questions about what just happened? Okay. Back to the slides. Now, oh, yeah, okay, let's go back and look at that again. Sorry. I want you to notice now, while he does this, what happens to the policy, which is, these little diamonds that are saying which way to go. So notice there's very little, these estimates here are all zero, so they've got a ways to go. Watch what happens to the policy, that is these blue arrows, as he iterates it. And let me see, get up to where he starts to do that.
See, the value functions start to take shape as we do more and more steps of value iteration. Again, 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 and again, and again, and again, and again, and again, and again. The numbers are starting. Not changing.
So the thing that you watch is notice that long before we've got the right values, they get pretty stable. So there's a few here that put that, but most of them are already in their final. The policy is converged. The point is, the policy is converged before the values have converged. So let's watch a little more.
I press it a lot.
And see that the policy is not changing at all.
Yeah, now they're that's a little less than 10. This is 0.7 times less than 10. So you can see the value.
So watch that again. Watch these again.
Again, and again, and again, and again, and again, and again.
This guy's flipping. Very subtle.
Changing that much.
And so the guy here said, "Oh, I should look down here." But now they're learning there's a better goal here, and they start to move away from this and head down to here. So this is going to depend on things like the reward in each state and the size of the factor. But it could be better to go over here and get an A than go to the rave up here and get a B in 150. Okay. So what this slide is showing is that the policy converges much faster than values. So if we look at this, values converge maybe around here, around 15 iterations. But here, the policy walk, the difference between what you followed the best policy versus what you get by following the best policy is gone to 0 by step 4. It's a very small world, but you know that's why this happens in part. Whereas this is the error in the value iteration, it's taking a lot longer to converge. Okay, so that brings up the idea of maybe we should try improving the policy instead of trying to improve the values. So that leads us to policy iteration. So policy iteration alternates 2 steps. One is policy evaluation, which is computing the values of each state given that you're following this policy. So the Bellman equations converge to the optimal values. But if I'm not following the optimal policy, I'll also have values for each state that depend on that policy. Once you've done that, and so this is actually solving something very similar to the Bellman equations, which we'll see in a moment. And then we use those new values to update the policy. And we go back and forth between these 2 steps. So again, policy evaluation is given a policy, calculate the utility of every state, given that we follow that policy. And, excuse me. Gotta tell my wife that I can't talk right here. Okay, so again, let's look at, okay, and then we've got the value, the values based on this policy, and now given those values, recalculate the policy by, from every state, figuring out the expected utility for each one state and take the action that maximizes that. Okay? So, the interesting thing about this is that we now have linear Bellman equations because we're following a particular policy. Look at these here's the Bellman equation. It's got a max in there. It says take the action that maximizes, it's the max over the actions of the action that maximizes my expected utility from one step. But if we're not trying to find the best one, then this action here is going to depend on our policy. And so instead of the standard Bellman equations, we get this one. So where the action is actually the action we take because of that policy. There's no max anymore. So now these are linear equations. N, if we have n states, this is n equations and n unknowns. Quick class poll. What are the unknowns? Raise your hand, and Panchu will watch you. Is this unknown? Okay, vote for that. Who thinks this is unknown? Vote for that. Who thinks this is unknown? Vote for that. Okay, I hope almost everybody raised their hand for this last one. These are the unknowns. These are the x's in our linear equations. And so that's what we're solving for. Panchu, did most of them get it right?
Some of them.
Really? Just some?
Most people, I mean, didn't raise their hand.
No, you can't not play. This is an MDP. You have to choose an action. And raising a hand isn't one of them. Not raising your hand. Okay. Those are fixed. Those are given to us by the MDP. Gamma is the discount factor. That's, somebody chose that. This is the transition function. It's the probability of getting to the next state given I'm in this state and I take this action. Okay, so that's not unknown. What's unknown here are the utilities. That's why we're doing this. We're trying to solve for these utilities, and they're on both sides of the equation. So it's a set of n linear equations, n being the number of states. So there's a utility of a state on the left-hand side. So there's going to be one of these for the first state, one for the second state, et cetera, et cetera. So there are n equations, and the unknowns are also n, the utilities of the states. Okay? That's what we're solving for. Equations with the max in there, we were solving for the optimal ones, and it wasn't a linear equation, so we couldn't just solve. So we did this iteration to solve it. And that's what that movie was showing, okay? So now we have n linear equations and n unknowns, these guys, and these guys. So we can just solve that. We have n equations, n unknowns. We invert a matrix from linear algebra that you took before you got to here, and solve. Period. We're done. Boom. Then we have a new estimate of the utilities of the states based on the policy we were following. But that policy may not be a really good policy, but it tells us about the utilities of the states, and it's just actually going to be, okay, so what the surprising thing about this is we've got these bad estimates of the utilities, then we improve our policy using those and iterate, and this actually converges also. Okay. So this is policy iteration. You evaluate your policy, your current policy. That gives you a new set of utilities. If it's okay, so unchanged is true initially. And then we go for each state in S, if there's an action, this is policy improvement right here. These steps right here, improving the policy. Let me just check. Okay. So if there's an action that gives us an expected utility that's higher than the one from the policy we're following, okay, if there's another action that's better than this one, then we update the policy for that state to that value. So this is a little stupid algorithm because it computes this twice, but That's what it does. Okay, so the policy is really just this, here it's just an array, or a vector even, of the states, based on the states, and we're sticking in the action that is the best one right now. If we got into here, if there was an action that was better than the current action we're taking, then we changed the policy. And so we put unchanged false. And this repeats until unchanged is true, and we're done. The policy is converged. Okay? So that's it. Then we go back and we do this big matrix inversion to find the new utilities. Okay? Then we set our unchanged variable to true. And then for each state, we look to see if there's a better action out of this state given these new utilities. And then if there is a better action, we update the policy and we say, oh, we changed it, loop. So we do this for all the states first, and then we go loop if we change the policy at all.
Hi, Gary.
That's the iteration. Yeah.
Connections just lost. Yeah, back again. So I'm not sure where we lost the connection, but can you start from like 1 minute ago?
So does this look familiar?
Sorry.
Does this slide look familiar?
Yeah, maybe you can start from here, I guess.
Okay.
Yeah, sorry about
that. So again, policy iteration alternates these two steps, and the shocking thing is that this thing converges because we change one thing, then we change the other thing. We change this thing, then we change the other thing. And evaluating the policy just means finding the utilities that we would get if we followed this policy. And then policy improvement means improving the policy based on those new values. Now the Bellman equations are linear because we're not choosing the best action, we're choosing the action based on this policy. So there's no max out here. There's just the policy that we're following. And that's why there's this pi up here. It's the utilities if we follow pi. And so again, now we have n equations and n unknowns. I've said this about a gazillion times now. I don't know how many times you've heard it. We have n linear equations and n unknowns, and we can just invert a matrix and solve it as the linear algebra course. And so now policy improvement uses these new values to create the new policy, and we iterate. So here it is. You start with some policy, which could be random initially, just some. So policy here is a vector indexed by the state. So not the totalitarian state, but the state of the MDP. And so policy is a vector, and for every state, the element of that vector is the action we take in that state, just a function. And so we evaluate, get some utility based on the policy. So this really should be pi. We assume we haven't changed the policy yet. And then for every state, we check, is there an action that gives, is there an action that gives us a better expected utility if we take that action from the state than the one in the current policy. So again, both of these are the expected utility of taking this action in this state. It's the sum over the probability of whatever next state we might get to times the utility of that next state. So it's the weighted sum. This is, again, the transition function. The weighted sum over the utilities of the next states we could get to. And if we have one that's better than that, then we should change the policy. That spot in this policy vector, the action that maximizes that quantity. And so this is kind of a stupid algorithm because it computes this twice, up here and down here, but I'm sure you can do better. And now we've changed the policy. So the policy is not unchanged. And when we go around it, then we go around again. We evaluate the new policy. We check to see if there's any better actions in each state. If there is one, we update the state and we keep track of the fact that we just changed the policy. Okay, that's it. And when the policy stops changing, we return that. That's called policy iteration. Okay. So often the state space is really, really big. This little grid world is used in AI classes because the state space is so small. But if the state space is like 1,000 states, then we're going to have 1,000 equations and 1,000 unknowns, and we're going to have to invert a matrix that's 1,000 by 1,000. And that's, just not something I want to do today. So instead, you can do an approximation to policy evaluation, which is this thing of figuring out the new utilities. The new ones will often not be far from the old ones. So instead of what we do is instead of doing a cold start where we start with all the utilities being 0, we start from the old utilities. So we do a warm start, as it were, and we iterate the equations as an update step. Now, instead of, just like the standard Bellman equations with the max in there, update state equation for some small number of steps. So this now becomes an assignment statement. All the utilities and update them, and then we plug them in the right-hand side and do it again. And it will converge very quickly, usually, because the policy usually doesn't change very much, so the values don't change very much. That's called modified policy iteration. And there it says that. And that often converges much faster than value iteration, which is what we started this lecture with, or standard policy iteration, which is the one where you invert the matrix. And then finally, there's asynchronous policy or value iteration that also works, where you just pick some subset of states and iterate on those. As long as you pick those in such a way that every state eventually gets updated, this works. Opens the door to heuristics again. So pick states near the goal first might be a good heuristic, for example, because those are the ones that are going to converge the quickest, and then maybe we should pick some ones a little farther away, etc. Okay, so that's MDP. We have two ways of solving them: value iteration and policy iteration. And policy iteration has these kind of more heuristic versions of themselves. where you just use the Bellman equations with the policy in there, and you just update them. Okay, so that leaves us with POM-DPs, which I promised you I'd tell you about. I'm not going to tell you very much about them, but because they're kind of beyond the scope of this course. But basically, it's an MDP where you can't actually see the state you're in. So instead, what you have is a sensor model. You have a probability of some evidence given the state you're in. This is your observation. So it might be like the number of walls next to you. That tells you something about where you are in this world, but it doesn't tell you what state you're in. So now we no longer know what state we're in, and we only have a belief state, which is a distribution over the states. So initially, we might not, if we get started in any state, and it's not the final state, then this distribution over the states is the kind of least informative prior. It's that we don't know anything about where we are. We just know we're not in a final state. Because if we were, we'd be dead, and so we wouldn't sense anything. So this is a uniform distribution over the 9 states that aren't the final states. Now, the agent can calculate its current belief state as the conditional probability distribution over the actual states given the sequence of percepts and actions so far. So if B of S is the previous belief state, and the agent does action A, and then perceives evidence E, then the new belief state is given by this equation. This is, again, a normalization factor. Oh, because this is a PDF, it's a probability distribution function, or in this case, a probability mass function. It's the probability of the evidence that we see, given that we were in state S prime, times this thing, which looks somewhat familiar, but it's not quite the same as what we've been doing. This is the transition function. This is the belief states that are belief distribution. So if our transition function is an expected next state. This is basically the expected, this is going to give a distribution over next states, given our belief of how much we believe we're in each state. And then that's S prime. So that's all the ways that we could get to S prime if we take action A. And then we get some evidence based on S prime. And evidence from different states could be similar. They don't give you, hey, you're in X, comma Y. They say, hey, there's a wall to your left. Something like that. And that doesn't tell you exactly what state you're in. So you really have, again, a probability distribution over your states. And this turns out to be something from chapter 15. Remember I said we were skipping it, but we do a little bit of it. This is based on a partially observable Markov process. So it's also called a hidden Markov model because we don't see the states. What we see instead is this observation from the states. The rest of it's Markovian. Whatever state we're in a discrete state, and we move to the next state depending on our action, but we don't get to see the next state. All we get to see is this observation. But you could, for the moment, instead treat the belief state as the state and solve the POM-DP as if it was a MDP on the belief state. So I'm going to talk more about that next time. But for now, we can treat the belief state as a state and solve the POMDP as if it was an MDP. What's wrong with that idea? I mean, there's nothing wrong with it really, but the problem is that now the state is continuous and no longer discrete. And that makes it hard. Really hard. And in fact, they're like, I don't know, p-space complete or something like that. So it's awful. It's not, and so one of the hard problems that we have that is still a really big, it's a really big research area. Okay, and that's it for today.
Thank you, Gary. See you on Friday.
Yep. In the flesh.